Hello, and welcome to an extension of Lesson 1.3. Lesson 1.3, we explore function transformations, right? We learn all of the different ways that our functions can be moved around or reflected or stretched, dilated, right? I wanted to make this video to include a few more examples that might help you out with the homework, yeah? Because that lesson, it really just did simple transformations, but we're kind of putting all of this together, right? And so this video, I'm going to work through three examples of three different functions. Oh, here's the third one right there. And just, kind of go through those. So, if there's any one that might help you, feel free to kind of poke around and watch any one of these three. So, at the top, I went ahead and typed the same instructions that are on your homework because the expectation is what we're going to do is we're going to look at this equation that's given. We're going to identify the transformations based off that equation, and then we're going to make a graph from there, and then from that graph, we'll analyze its features, yeah? And on this graph, the specification or expectation is that you graph at least 3 points. And I'm going to spend some time talking about how do you find good points, right? Because to find points, you just plug numbers in. But depending on the number you plug in, you might get something ugly, right? Something like the 1.236, right? I don't know. I don't want something like that. I want some nice, pretty coordinates, yeah, that'll lie on the graph. So let's start with this first one. Example 1, I've got a quadratic function. What tells me that this is quadratic? Boop, right there. Little exponent of 2 tells me that the parent function, in this example, let's go to red here, is x squared. This is a quadratic function. And I know from lesson 1.2, looking at all the parent functions that we have, x squared makes a U-shaped, this is called a parabola, yeah? So this is our parabola. And based off the transformations, right, this parabola, it might get really skinny, it might get really wide, it might move, it might flip upside down, right? So we might do multiple transformations to this parabola, and that's what we're going to see. Now, from class, you should have a one-pager that describes all the transformations. I don't have it pulled up in this video, but for reference, I will write it right here. The one-pager describes function transformations as a times f of b multiplying x minus c, and then there's a plus d at the end. I do expect that you've seen that video, that you've kind of reviewed that one-pager before kind of proceeding with this, because that's a lot of information to go over here. I just want to give you some examples, right? But each one of these letters, A, B, C, and D, do different transformations. To recap, the value of A, a constant, affects vertical its vertical features, but in particular, its stretching. So if you had a parabola, you could stretch it vertically, or you could compress it vertically, yeah? You could also reflect it upside down, and the A value would do that. The B value is similar, but it's all the same things horizontally. So if you had a parabola, you could horizontally compress it, which would mean to squeeze it to the insides, which might kind of look like this, or pull it outwards, which means it might look more flatlined like this, yeah? If B was negative, that's also a horizontal reflection, although with a parabola, right, since it's symmetrical, you're not really going to see that. Something that could be symmetrical, maybe like a square root curve, right? If you reflect that horizontally, it'll look like this. So that's what the B value does. And then this part that says x minus c, this moves it left and right, and the plus d moves it up and down. So those are translations, yeah? For a quadratic, our function with this general format of a, b, c, d, a quadratic function would look like a multiplying b times x minus c, and then this quantity is squared, and then there's plus d on the outside. Yeah. Now, the reason I take a time to talk about that and write it like that is I recommend, since you're first starting this out, especially if you're struggling with it, to write this, the general format here, write the specific format for whatever function you're talking about. In this case, we're talking about x squared, so this would be the format for that. And then right underneath this, rewrite what you see here. Because it should kind of line up and let you know which value is which value. So it says 3 halves, x plus 4, right? So I'm going to say 3 halves, x plus 4 squared, and then a minus 2 at the end there. Yeah? See, the reason I like this is it kind of lines up your A, B, C, D. Yeah? I'm hoping that you can see that the 3 halves is present on the outside of these parentheses here. That means that's the A value. Right? The B value multiplies x and c, but there's no B value seemingly next to this x. It says x minus c, so x plus 4, okay. And then minus 2 is like the plus d at the end, yeah? So you can see all of the transformations kind of just writing it right beneath like this, yeah? To note this down, I'll say, okay, A is 3 halves. C, so since it says x minus c, but this says x plus 4, right? That means you're doing x minus negative 4, which is becoming x plus 4. So the c value itself is negative 4, and the d value is negative 2. So seeing that, what you would do is note this down and then look at your one-pager because it has information about what these values mean. And I'll just go ahead and tell you, A is 3 halves. So I'm going to say, since A is 3 halves, which is more than 1, this means you have a vertical stretch. That is that transformation. And again, if that's the parent function, then the stretch will look something like this. Then the c value, right? It says c equals negative 4. I'm going to say, since c equals negative 4, this is going to shift left. I'm going to specify 4 units. Yeah. If it says x plus 4, that moves left. If it said x minus 4, this would move right. Yeah. We see that on the one-pager. And then lastly here, d equals negative 2. So I'm going to say since d equals negative 2, this will shift down 2 units. Okay? And so those are all the transformations described. And we get those transformations by really memorizing the format of these and then knowing their association. You know, what do these quantities mean? We can see them once we graph it, but we actually want to build the ability to know the transformations just by looking at the equation, not just seeing the graph. But now we can make the graph. Yeah, now that we have these transformations, we're going to make the graph. But we need points, right? And at the start of the video, I mentioned you want to find a nice creative way to find points. You don't want to just plug in things randomly, right? Like if I want to make x 10, well, then 10 plus 4 is 14, which squared is, I don't like that, right? I don't want to square 14. So what are good numbers to pick so that I'm not just plugging things in totally at random? Well, the first thing I would think about, and the value in finding your transformations first, is to help you figure out what a key point or a key attribute on the graph. So in 1.2, all of our parent functions kind of have a key point on them. So for parabolas, it's a vertex. It's the same is true for absolute value. It's a vertex. So when we talk about those two functions, my key point that I'm interested in, affected by transformations, is the vertex. For a cubic function and its cube root, it's what's called the inflection point, is probably the key point there. We're also missing square root, which would have an endpoint. And then for the other last three, Exponential, it's not a point, but it's an asymptote. Logarithmic, also an asymptote. And rational is two asymptotes. So they're not points, but they're key features, yeah? And those transformations directly affect those features, particularly your shifting left, right, up, and down. So if you know that the parent function of a quadratic, right, maybe if I just to kind of sketch it here, looks something like this. That's a very rough sketch, but its vertex is at 0, 0, right? That's at the origin. If I look at the transformations, I have shifted this left 4 units, down 2 units. So that vertex at 0, 0 will shift left 4 units, then down 2 units, meaning my first point of the vertex actually is going to be at -4, -2. So I'm actually going to write that down now, -4, -2. And that is my first point on the parabola, like so. Not only is that the first point, that is in particular the vertex, which I might note real quick right here, -4, comma, -2, okay? Now, the reason I like to find this point first is I would find this key feature, this key point, and then just plug in numbers close to that, yeah? Just maybe increments of 1 or 2 away. So the point that would be after -4 would be -3, right? And so I could plug this in. Now, what do I mean by plug in the point, right? Well, f of x is 3/2 times x plus 4 squared minus 2, right? When I say plug in x, I'm saying evaluate f of, let's say, -4, right? Then that means to replace x with -4 directly into the equation and then compute it. So do the math, right? This is always going to use order of operations. So think about PEMDAS, if you've heard that acronym, right? Parentheses, exponents, multiplication, division, addition, subtraction. In this example, -4 plus 4 is 0. Squared is 0. 3/2 times 0 is 0. And then minus 2 is -2. So you see you started with -4, but you end up with -2, which is what we have on this graph. We found that one from transformations though, right? But if I wanted to evaluate f of -3, that would just be doing the same thing, but replacing it with a -3. And I'm going to actually write out the math this time. If you do order of operations, -3 plus 4 is 1. And then that's going to get squared, which is just 1. Meaning it's just 3/2 times 1. That's just itself. Minus 2. Of course, 3/2 is like 1.5. Subtract 2 from 1.5 and you have -0.5. Yeah? Or you could write -0.5 there. So at -3, -0.5, that's going to be about right there. You might say, Mr. Spake, is it okay for me to have fractions in my table? And I would say, yeah, that's fine. But try to keep them nice, fractions, like 0.5, a half, whatever. I'm not sure we would like to see something like 17/20ths, right? I don't know if I want to see anything like that, right? But anyway, there's a point. Let's find another one. I said plug in numbers close to -4. Well, another number close to -4 would be -2. And so I'm going to just do the same thing again, right? F of -2 is 3/2 times -2 plus 4 squared minus 2, right? Order of operations, I'll write that again. I would just say, okay, well, -2 plus 4 is 2. This value is going to get squared, which means it's 3/2 times 4, then subtracting 2. 3 times 4 is 12. Notice 3/2 times 4, right? If you do 3 times 4 on top, you get 12 over 2, which is 6. So I would get a 6 here. And then subtract 2, getting me 4. So I got -2 comma 4. Yeah? -2 comma 4. Boom. Nice. And so I've got some points here, yeah? Could I go on to -1? Yes, I could, but that's 3 points, right? And the expectation was 3 points, so I've accomplished my goal. But there's a bit of a problem here. I know that the parent function is this parabolic shape, this U shape, right? It's a parabola. If I just connect these 3 points, well, that doesn't show me a parabola, right? So I'm missing something. I want to make, I have my 3 points, but it needs to look like the parent function. Well, something that's nice about knowing where the vertex is the vertex marks symmetry. You see, on a parabola like this, the axis of symmetry runs right through the vertex. So, where's the axis of symmetry here? It looks like it's right down the middle here. Because if you recall, this point, -4, -2, was the vertex. And why I like that is because now that I have this axis of symmetry, I can simply mirror the points over, and this will get me basically the other side of the parabola. And so, ta-da, I've got all my points like this. And now with a smooth curve, it's a little hard for me on iPad, so I'm going to kind of do these little dashes here. I could do a lot better on paper and pencil, but I'm not the best with my iPad here. Then I'm going to kind of come up like this, as smooth as I can. Extending upwards like this. Yeah, there it is. Okay, you know what, just because I want to make that a little nicer. Just a little nicer. Whoop, 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 whoop. Okay, all right. And there's my parabola. Not the best, but decent. It's decent. Okay, and so now that I see this parabola, I mean, I can think about, do the transformations kind of make sense now that I can see the image? A parabola, this one's vertically stretched, but only by a little bit. An original one would look something like this. Oops. Something like that. And so this does seem slightly skinnier, right? So it's vertically stretched, moved left 4, down 2. Looking at the image, I'm going to read domain and range. So domain, left and right. These 2 arrows imply both going upwards, but also left. Yeah. So this is going left forever here, and this one's going right forever here. So the end behavior is going to infinity for, well, I shouldn't say that because of whatever. X is going left to infinity and right to infinity, and there's no interruptions on this graph, which is to say that the domain is all real numbers. It's everything, right? So I say negative infinity to positive infinity. Oh, by the way, I guess I didn't fill out that table, huh? -5 looks like that would be the -0.5, and -6 would be the 4. Anyway, so that is handled there. And then the range, right? Range is least to greatest. So we read the y values from the bottom, and we go all the way up to the top, right? Well, the lowest point on this graph is right here, and that y value is -3. And the graph extends upwards forever, so it's going to be everything from -3 up to infinity, yeah? So I'm going to say bracket -3 to infinity. And that is example 1, my quadratic function. Yeah? Okay, so that's that one. And that's breaking down the transformations, drawing the graph, analyzing the features, right? The really new part is graphing it and knowing what the transformations are. Okay, let's do example 2. I'm going to switch to blue just because. Why not? Yeah, just separate the math a little bit. This one looks like a lot of stuff. I guess we'll see what happens. Well, I'm going to start off with the same thing I did last time, which is first identify the parent function. That's square root x. And I do know that a square root x function looks something like that, right? That's what the parent function looks like, kind of curved there. Yeah? So I know when I graph this, I need to know an endpoint, and I need to know where it's facing, right? Now, like the last one, I'm going to write a times f of b times x minus c plus d, right? These are general function transformations. But in particular, for a square root function, f, the function, is square root x. So the inside of this is b times x minus c, and on the outside is a, and then plus d right here. Now that I have that, I'm going to write the function right below. So it looks like it's negative 4x minus 20 plus 5. Okay, let's write that. Negative square root 4x minus 20 plus 5. Okay. So I'm going to lasso this one. Ooh, come here, you. Round him up. There he is. Okay. Now, we're going to notice something. And I'm going to really zoom in here. So this takes up your entire screen, yeah? This example is tricky, and I made it tricky for a particular reason, so you know to look out for it. And it has to do with the interior of the root symbol, the radical, yeah? If you look at this, it says 4x minus 20. But if you look right here, it says b times x minus c. So what's different about this and this? Well, this expression has parentheses in it. I am not observing any parentheses in this expression, right? So what's really going on here is, and if you remember distribution, right? Example, if you said 2 times x minus 2, right? Then if you multiply this, you distribute it, you would get 2x minus 4. So the problem is this is currently written as it's distributed. I need to write it in what's called factored form, which is to say I need to pull the GCF out, yeah? So if I'm looking at this, right, I just say this. So it's negative square root. I'm sorry, I don't like that square root. Ugly. Let's try a better one. Oh, okay, that's fine. I can see that, b and x, the b multiplying x, this is going to be that 4. So I know that the b value is 4, and then that would put x here. Oops. But then what would 20 become, right? Because it's not going to stay 20. It's going to change because this 4 multiplies x, but then it also multiplies whatever this number is. So you just have to ask yourself, if you pull out 4, which is to say you factor out 4, what does 20 become? Well, thinking forward, 4 times negative 5 would get you negative 20. So that's what goes in there, minus 5. And then there's my plus 5 at the end, yeah? So now I can identify every last transformation that's present here, yeah? The first thing I'll notice is the a value is that negative sign. Notice that there's no number, it's just the negative sign. That means a is negative 1 because there's always a 1 multiplying as a coefficient. Now that I've written it as this form, I can see that the b value is 4. And I can see, it says x minus c. This says x minus 5. So c is 5. And d is also 5 because it's just plus d, right, which is plus 5. So I have 4 transformations happening here, right? So as a sentence, since a is negative 1, right? The fact that it's negative, if you look at that one pager of transformations, this would tell us that this is a vertical reflection for the a value, yeah? Look at the one pager again and look at for the b value. It says if b equals 4, this is going to be classified as a horizontal compression. That's what that transformation does. And by the way, if I wanted to be in particular, the full sentence would say horizontal compression by a factor of 1/4. Now, to explain that, right? This says 4, this says 1/4. Mr. Spake, what gives? If you describe something as a compression, then it's being compressed by a fraction or divided. Now, I know it looks like multiplication, right, because it's 4 times x, but that's just kind of how that works. Up here, I guess I didn't quite say it. This was a vertical stretch by a factor of 3/2, just because a was more than 1. Like, it was a stretch, so it just is the number. Whereas if it's a compression, it's kind of the reciprocal of whatever the number was. So anyway, that's picky, okay? And if you were to say horizontal compression, I think that's pretty good, yeah? That's pretty good. I'm pretty happy with that, okay? C is 5, so since C is 5, this is going to shift to the right. And lastly, since D is 5, it's going to shift up. And I suppose I should say by 5 units. Each of those is going to be by 5 units. We would prefer you specify just exactly how much it's moving up or whatnot, yeah? Okay, so there's the transformations. Personally, I think that's the hardest part. I think memorizing the rules and then looking at the equation, figuring out, I think that's the hardest part. But, as everyone, has their own opinion on what. Now we got to make the graph, which I think is the fun part. Yes, graph time. So just like the parabola, right? Just like we did the previous example, I mentioned that you can find your first point from the shifts of the function. And in particular, there's a key attribute or a key point you're looking for. For a square root function, it's its endpoint. You see, the parent function is going to look something like this, more or less, a little bit like that, yeah? That's the parent function square root graph, and its endpoint is at the origin, 0, 0. So where are we moving it? We are moving it right 5, up 5. So this is going to move from 0, 0 to the right by 5, and up 5 by 5, placing, right here is where our new endpoint is going to be. So it's at 5, 5. Boop. That's our first ordered pair. Now that you have this, just start plugging in stuff, yeah? It's up to you on what you want to plug in. But do pay attention that we're with a square root here, and you can't take the square root of negatives because they don't give you real numbers. So be careful here because you don't want to take the square root of a negative. Example, I don't really want to pick something like 3 because 3 minus 5 is negative 2. And so, that kind of, I'm going to be taking the square root of a negative. I don't really want to do that, okay? So, what can we plug in? Well, let's plug in something close to 5, right? Close to 5 would be like 6, okay. So I'm going to say, where can I find some room here? Yeah, here, right here. I say f of x is, negative root. And by the way, it's cool to use either of these forms. You can either use the factored form or you can use the fully multiplied form. Doesn't really matter. I'm going to do the factored form. I think the math works out a little bit easier. So 4 times x minus 5, and then there's a plus 5 here. And the first number I'm going to try is 6. So I'm going to do negative square root of, now this is 6 minus 5 in those parentheses. Now remember, it's just PEMDAS. It's order of operations. So 6 minus 5 is 1, which means it's just 4 times 1, right? And notice you're doing 4 times 1. Well, that's just 4. Square root of 4 is 2. But there's a negative here. So that is going to become negative 2, which when added with 5 is 3. So if I put in 6, I get out, the output is 3. But I go to 6 and put 3. Yeah? I think that's right. I didn't mess anything up, right? I don't think so. I think I'm okay. I'm just double checking, guys. Just making sure here. And now I need to, try something else, right? I need to try something else. I wonder, what do I want to try? So square roots can be tricky because you want to take the square root of perfect squares. Example, square root of 0, square root of 1, square root of 4, square root of 9, square root of 16, right? We would like the numbers to be those. If you were to pick the number 7, right? If you pick 7 here, I'm not going to write all the math, but 7 minus 5 is 2, and 4 times 2 is 8. I don't know the square root of 8, right? So I would have to say, okay, I wouldn't pick 7 because I don't know the square root of 8. And then the question would be, what can I plug in for x to make it any one of these, right? Any one of those. If I plug in 5, 5 minus 5 is 0, so that would get you the square root 0 happening, but we already have 5. And 6 helped us get the square root of 4. So you have to think, I could maybe get square root of 1, but that would involve a fraction. I don't know if we want to do that. Maybe square root of 16, because that's an even number, right? If the inside of the square root says, 4 times number, and I wanted it to be 16, then I would just need to make that number a 4. That number that I'm talking about is this x minus 5. We want to make that a 4. So what number minus 5 is 4? Answer, 9. That's the next number we're going to plug in, right? So, again, if you're not following me there, if you're like, Mr. Bake, no worries. Don't worry too much about that. Just plug in stuff, and it doesn't look nice, pick a different number, yeah? But if you are, then you say, oh, okay, I see that, right? That's actually going to end up saving me more time so that I don't have to plug in a bunch of random numbers, yeah? So let's try 9 now. F of 9, we got a negative root. We got 4 times 9 minus 5 plus 5. So this would become 4 times 4, which that was the goal, right? So it's negative root 16 plus 5. Of course, square root of 16 is 4. So that's a negative 4 plus 5, getting me 1 is the answer, 1. So 9 comma 1 is our next point right there. Beautiful. That's 3 points. So I'm going to connect my smooth curve there. Ooh, that was pretty swell. That was pretty good. And if I look at my transformations, right? Vertical reflection, horizontal compression, shift right, shift up. Yeah, that kind of looks like that. Yeah, it kind of looks like that. I could see my endpoint is at 5, 5, so I'll note that. Now, reading domain and range, this is fun. Domain goes left and right, so your domain, the leftmost x value, right, is right here is the leftmost point. It's at negative 5. It goes all the way to the right, which means it goes to infinity. So, domain, bracket 5 to positive infinity. That's our domain. As for range, right, I say lowest all the way up to highest. So I think, how low does it go? So, well, there's an arrow here pointing down forever. So it's going to be coming from negative infinity up, until this value, the highest point on the graph, which is at 5. So the range is negative infinity up to 5. And so the square root curve is graphed. That is a really solid example. I'll let you know, students, if you can do that, you can do anything. Because that is every single transformation kind of variation, right? That's a shift left and right, up and down. There's a compression factor and there's a reflection factor, right? Those are the three transformations you would encounter. We encountered all three of them here. Yeah, that's a good one. That's a really good question. Cool. All right, I've got one more example for you. And really, these first two examples are solid, but I wanted to show one also with an asymptote. And so this is the last one I do for this video, and I chose an exponential function. So the parent function, right, is exponential. So what's giving this away? Exponential functions are of the format b to the x. When I say b, I'm talking about a base, right? Which means you pick a number. So it's like 2 to the x, it's 3 to the x, it's 4 to the x, it's 10 to the x, right? Any one of those is an exponential function. In this instance, I've got a 4 to the x there, yeah? So the exponential parent function is 4 to the power of x. The base is 4. And an exponential function looks something like this. And its key attribute is that it has an asymptote, okay? That's why I'd like to analyze this, because this one has an asymptote, and I want to see how that works, yeah? Okay, well, let's start off with the same situation. I'm going to draw, or write the general function format of transformations, and I'm going to write it again, but for an exponential function in base 4. So the base is 4, the power is x, but x is the input, and the input is b times x minus c. The a value would be multiplying on the outside next to the 4, and plus d would be right over there, okay? I think for students, exponential functions are maybe probably the most tricky ones, because it's kind of weird having the horizontal transformations up in an exponent, those little tiny numbers. But that's it. That's the equivalent form for exponentials. So if I'm gonna look at this again and rewrite it, see here, a half, negative x and minus 3. So it is 1/2 times 4 to the negative x minus 3. And again, I'm just going to look at all these values and relate them to a, b, c, d. The a value is a half. That's what's multiplying it. So it's a equals 1/2. Then you see up in the exponent here, it just says negative x, nothing else. So it doesn't say like x plus 2 or like x minus 3, right? So it's not x minus c. It's really just bx. And what is b? B is a negative. In particular, b is negative 1. And lastly, plus d, that is minus 3. Okay? So I got a is a half, b is negative 1, d is negative 3. So, since a is a half, right? Look at your transformation sheet, the little rules. If a is a half, which is less than 1, well, in particular between 0 and 1, then this means we have a vertical compression. And I would say that this is by a factor of 1/2. Yeah, that's my vertical compression by. And remember, I said earlier that a stretch, that's always going to be like a whole number. Compression will be a fraction, right? So this is a half, this is a half. But on the previous page, horizontal compression, that was a 4, but it needed to be a fraction, 1/4, if that makes sense. I hope that's not too confusing. I know it's a little strange, though. So if you're like, don't sweat it too much. What else did I know? I said b, I think the b value was negative 1. If the a value is negative 1, that would be a vertical reflection. So if the b value is negative 1, this is a horizontal reflection. which, if your if your exponential looks like this, then to horizontally reflect it means it to look like this. It's going to come down like that. And then I also said, I think that D was -3. D equals -3. This will shift down 3 units. Yes. Okay. Now it's time to plug in points. And for an exponential, this would be a little tricky. It can be. This one's actually pretty simple, mainly because it doesn't have there's no shifting left or right. But exponential doesn't really have a key point. It does have a y-intercept, but the y-intercept isn't necessarily, I don't want to call it immutable, but for other functions, so when it's an inflection point or if it's a vertex, the only thing that changes those specifically is shifting left and right, but any other point on the curve is subject to change from stretching, right, or reflecting. So you can't really use a y-intercept like that because it's not really a key feature. It is a feature, but it's not like a defining attribute, yeah? A defining attribute of this function is its asymptote. Now, its asymptote here, where is an exponential function's asymptote? So, well, this is the exponential. Its asymptote is at y equals 0. But we have moved this function down 3. So that would take this horizontal asymptote and move it down 3 units, making it y equals -3. Okay? So I'm actually going to go ahead and write that. The asymptote is y equals -3. All right. There it is. That's my asymptote. Okay? But notice how that doesn't really help me plug in points because the asymptote isn't a point, right? In fact, this asymptote, the graph doesn't even touch it. So what the heck, right? What do I do? Well, now I'm just going to plug in points, but I'm going to think carefully about what would work well with the exponents, yeah? Notice it says 4 to the -x, yeah? So if I say f of x is 1/2 times 4 to the -x minus 3, let's do f of 0. That one's easy. Plugging in 0 is always nice because -0 is just 0. So 4 to the 0th power, anything to the 0th power is 1. So this gets me 1/2 times 1 minus 3. Of course, half minus 3 is -2.5. I'm just going to do those dead, right? It's 0.5 minus 3, that's -2.5. So if you plug in 0, you get -2.5. Okay? Say 0, -2.5. Right there. Pretty close to that asymptote, yeah? Now let's try some other ones. Now you might be tempted to plug in 1, right? And that's okay. Like, it'll work, but I'm going to let you know that fraction is going to be pretty ugly. To do the math with you real quick, you did 1/2 times 4 to the -1 minus 3. Well, 4 to the -1 is actually a fraction. It's 1/4. So now you're doing 1/2 times 1/4. Ugh, that's an 1/8 minus 3. Ugh. What? You mean that's like -2 and 7/8? I don't like that. So I'm not going to pick 1. I could. I'm not going to. I'm going to pick -1. This will actually be more nice to me. If I plug in -1 to the function, then I'm going to get 1/2 times 4 to the -1 minus 3. Because remember, the power has a negative in it, and I'm plugging in a negative number. So now I'm going to do 1/2 times 4 to the 1, because a double negative is a positive, which really means it's just half of 4, which is 2, and 2 minus 3 is -1. Oh, nice. So I get -1, -1. Beautiful point right there. Yeah. The next point, I'll just go one lower, -2. So it's going to be a half times 4 to the -2 minus 3. This is half of 4 squared. Okay. But 4 squared, well, that's just 16. And half of 16 is 8. And 8 minus 3 is 5. So if I plug in -2, I end up getting 5. So -2, comma 5. That's 3 points and that beautiful asymptote. So I'm going to connect these points with a nice smooth line. Smooth as I can make on this little iPad I have. I do love my iPad. Okay. There it is. Ta-da! Nice. And I can see the exponential function right there. Yeah? And remember, earlier I said, hey, it looks like this, but you're horizontally reflecting, it's just going to look like that. Yeah, it looks like that, right? It comes from above down, like so. So, what's the domain? Domain is left and right forever. That's all real numbers. That's positive infinity to negative infinity. You can see this because of this arrow and this arrow, saying it goes left forever and right forever. And there's no interruptions along this graph. It's nice and continuous for that whole domain interval, so it's all real numbers. Your range, you think lowest to highest, there's no function below this asymptote, and that asymptote is at y is -3, right? So the lowest boundary is -3, but it's going up and up and up and up. So it's -3 to infinity. But if this is an asymptote for an exponential function, it's not going to touch that asymptote, so I'm going to do parenthesis 3, not bracket, because it's not going to touch -3. Yeah? And there you go. Yeah, there it is. That is 3 examples worked of transformations for a quadratic, a square root, and an exponential, which I think is pretty good. We talked about symmetry, right? If you have a graph that's symmetrical, like absolute value or quadratic, you can use its symmetry to find other points. Square roots, just keep in mind that there's going to be like a smallest point that you can plug in because it has an endpoint. So you want to think about where that endpoint is. Think about how the transformations affect that. And then exponential, logarithmic, and rational, their key features are asymptotes. So you would want to analyze your features first to know how the shifts affect your asymptotes. And then once you know that, well, then there you go. Now you have the idea where the asymptote is. So, okay. I hope this is helpful. Thank you for watching, and I'll see you around in these little videos.